We can already see back to the first visible stage in the universe, but a point in cosmic history that we can't yet see is something called the epoch of reionization. And this is the point in cosmic history when the first stars and galaxies were born. It's one of the key scientific questions in astrophysics at the moment, and AI is undoubtedly going to be an essential part of answering that.
At this AI for Science event, we've brought together researchers from a really diverse variety of fields to see how AI is really having an impact.
A lot of our complex physical systems require a lot of data, a lot of physical knowledge, and we need to be bringing those together, and AI for Science is a clear path to do that.
There aren't enough astronomers in the world to look at all the data by eye, and AI can help with that.
So the world needs new materials. So with AI, we have the chance to solve problems faster. We also have the chance to tackle problems that were impossible to solve before. So navigating large spaces of possible materials with specific properties.
So weather and climate is a hugely complex system. It's a fluid on a sphere on the Earth. And actually the AI that we might use for weather forecasting is very similar to the AI we might see in other areas, such as modeling the flow within batteries or in fusion technology.
We are already using AI to expedite the commercialization of use of fusion energy. And the way we're doing this is by having surrogate models and by using AI in plasma controls and by developing models based on current experimental data that can tell us what the plasma inside the machine is going to do in real time.
So we're moving from models that just run simulations to one that actually interact with real experiments. We have a feedback loop where experiments are performed. The model learns from those results and actually decides on the next experiment.
Going beyond what we know, I think is actually easier than you might expect, because if you set up your machine learning model to learn directly from data rather than learning from human labels, it can, discover things that we don't know.
AI, by its very nature, learns things that it sees a lot of better than things that it doesn't see a lot of. So preserving the potential for discovery is absolutely essential in astrophysics.
The very first thing that you have to do when you even start thinking about making AI models for science is how are you going to deploy them. Because if you make a really nice, very predictive model and nobody wants to use it because they don't trust it, you wasted time and energy and resources.
You've trained this model, it works well, but what did it actually learn? And I think that's something that's really important, and it's still kind of underdeveloped. Because if we're going to trust, a machine learning model in science, we really want to understand the predictions it's making.
So much of the AI work we're doing is we are developing on top of open source frameworks and contributing to that national effort and international effort. So it makes sense that we work collaboratively with AI for astrophysics, AI for materials, AI for battery technologies and plasma. There's a lot of shared information and ideas, and the fundamental research is helping to bring those together.
It's not just AI being applied in science, but also science feeding back into AI. And it's when we close that feedback loop that we can really expect to see remarkable progress.